Okay, welcome back to part two. You'll notice a change of scene because I'm down in the dungeon now because teenagers are home and it's quiet down here. So on with the show. Chapter 2, Standards, Messaging at layers 2, 3, and 4. We may not even get that far. I just want to set the stage with what standards are and why we have them, why they're important. The best way to talk about this, I think, is just in terms of how people communicate together. Like if you want to send a message from, Tim to Tom, we have to agree on certain things. We have to agree on the language, like English, and we have to agree on syntax, because otherwise, like Yoda, speak we. And the book talks about a standard being the same thing as a protocol, and I'm not quite sure I agree with that. It's fine for our purposes to blur the two, but to me a protocol is a set of rules for transmitting information. A protocol is a set of rules. A standard is something that's either accepted as a standard or it's not. It's certified or it's not. So to be more precise, TCP/IP is a standard protocol. There are other protocols. There are lots of other protocols that are not standard. For example, pigeons, carrier pigeons. There's actually an RFC for it, as you know now. I would not call that a standard protocol, but it is a protocol nevertheless. So I'll stick with the term protocol just because I prefer it. So like I said, a protocol is a set of rules that govern the exchange of messages. This includes message order, so think Yoda, and also think in terms of who speaks first. So the protocol, when you answer a phone, is you say hello first, and then the other person who called you says hello. It's awkward when it goes the other way. Semantics is meaning, the meaning of the words we're using, and syntax is the grammar. But then we have things like we care about reliability, whether the message gets through or not. So when we're communicating verbally, the phrase we use is "eh?" or "what?" when we want you to retransmit. And connection orientation means we care about whether if there's an ongoing conversation. So a telephone call is a great example of a connection-based conversation. And so long as we're on the phone together, we have a connection. And then when we're done talking, we release the connection. Whereas yelling something out on the side of the road at a pretty boy or girl, whistling at them and saying something rude, you don't care if the message got through or not. That's connectionless orientation. And so it's important to be comfortable with these definitions, and this is all we're talking about at this point. So the first one's message order. Like I said, telephone conversation, the order of messages matters, who initiates it. So in client server, obviously the client has to initiate the request. It'd be ridiculous if the servers were initiating requests and just sending out random responses to nobody's request. Maybe that's a silly example. Reliability corrects errors in transmission. I like to do an example in class where I get into the difference between error detection and error correction. I'll probably save that for class because it's going to stick with you better if I do it with you in person. Message order, request is sent, response comes back from the server. Things at layer 5 are connectionless in the sense that every request and response is independent. So you ask for a web page, you get that web page, that's it. If you need another web page, you have to open up another connection. Now, at layer 4 we care about connections, especially when we're doing file transfer. So we want to open up a connection, send a bunch of message fragments that constitute the entire file before we close the connection. We don't want to send part of the file, close the connection, open up another connection, then send the rest of the file. That would be, well, inefficient and very prone to errors. So there's a very formal opening of the connection and closing of the connection. And we'll get into an example. Opening a TCP connection is very formal. It begins with a handshake. This slide outlines the formal handshaking process. Host A wants to talk to host B, so it has to send a request. That first request is a request to synchronize, or a SYN request. It sends that to host B. Host B replies, I acknowledge your request to synchronize. I want to talk to you. Yes, I will talk to you. And then host A responds back, I acknowledge your acknowledgement that we are going to talk together. Now we have an open connection. Please do not forget, even though we're talking about how layer 4 talks to layer 4 from host A to host B, layer 4 does not talk directly to layer 4 on the other side. Because how does it go? It goes down the stack, over, and then up the stack. So we're just kind of abbreviating that process. It's assumed. So down the stack, up the stack. So on the other side here, once the handshake is complete, we've got an open connection. Now, host A is going to send some data, a request for a web page. And because host B did not immediately send an acknowledgement, because this is a connection-based protocol, host A is going to retransmit. This doesn't always happen, but we care about this in a connection-based protocol like TCP. So it's going to resend exactly the same message until it gets an acknowledgement. Host B responds, yes, I got that request that time, and here's the data you asked for, here's the web page you asked for, and then host A acknowledges, thank you. It's very polite. It's a very polite protocol. I received the information that I asked for. We're good. And as long as the connection is up and running, host A can continue to send requests, and host B will continue to send responses as long as that connection is open. Once we're done, we're ready to close the connection, ready to hang up the phone, if you will. There are 4 stages, 4 steps in closing a TCP connection with fin segments. So remember, we talk about segments because it's layer 4, not packets. The generic term would be messages back and forth. But a fin or finish segment, host A sends, I'm finished, I'm done. Host B responds with, I acknowledge that you're finished, and I'm going to send the last of the data. Here's the last data. Boom. That's it. I acknowledge that you sent me the last data. Boom. Now, host B is ready to close the connection and send its own finish message this way. So the first finish was this way, a bunch of stuff happened, and then B is now sending a finish command back to A. A acknowledges the finish, and now, boop, we're done. Just like that. The great thing about this process is, if it looks chatty, it is. So this protocol is sending SYN, ACK, FIN commands all the time over the network. You will see this. You will see this in your homework assignment number 2. When you're doing your packet capture assignment using Wireshark, you'll see SYN, FIN, ACK. You'll see them flying across your network. So why do I have gumdrops on this slide? Because it's sweet! So that was connection orientation. The next definition is semantics, the meaning of a message. So just like it is in the English language, the semantics is the meaning. We care less about this in networking because we just care about getting the commands to their destination. We actually don't really care what the contents are. End users care about what the contents are. So a get command, get this file, would be an example of semantics that has to be using the correct syntax. And all of these messages that are going back and forth, the different types of messages we're talking about, the basic syntax is that there are 3 parts. They don't necessarily correspond with noun, verb, object, but there might be some parallel. The 3 parts are a header, and really the header is probably the most useful part for network engineering. The data field, the contents of the message, and then sometimes there's a trailer on the message. But the header is going to be composed of multiple fields, and what's inside those fields is important. Some of the things inside a header, one of these header fields would be the source address, the destination address, the size of the message, maybe some checksum information. There's lots of potential fields. Even the version of the protocol that you're using might be in a header. But there are 3 basic parts. Sometimes we send a message that's a header only with no data in it whatsoever. Sometimes we send a header and data with no trailer. As far as I know, you don't send a trailer by itself because that would be ridiculous. Just another slide that shows the individual fields inside of the header section of the message. And I want you to get very comfortable with this vocabulary. If you are in doubt about what to refer to, you know there's a message going across the network, but you're not sure what layer it is, and you don't want to sound dumb, you can say the message. The message is a generic term. But if you want to be precise in your language, if you talk about a packet going across the network, you're absolutely talking about layer 3. Routing, IP addresses, that's layer 3. If you talk about a frame going across the network, you're talking about layer 2 from one switch to another, using MAC addresses. If you talk about a segment or datagram, but a segment going across at layer 4, so when you're talking to another networking person, this conveys very precise information, which is actually very helpful. Another important bit of vocabulary, and this is going to sound silly, I think, based on everybody's response in class, you're comfortable with the idea that there are 8 bits to a byte, and the vocabulary of talking about bits and bytes. Now, another name for a byte is an octet, because oct from the Latin for 8, 8 bits, and in networking, for some reason, we don't talk about bytes. We talk about octets. Why? It's just part of networking culture. I can't explain why, but if somebody refers to an octet, you know you're talking to a networking person, a hardware person. If somebody talks about bytes, you know you're talking to a software person or a programmer. So here's another example. I mentioned before that some messages don't have a data field, it's just a header. So the SYN segment we were talking about before in our example of handshaking is just a header with a lot of good information in the header, but there's no data. So when you're handshaking, there's no actual data to transmit yet. It's just part of the protocol in order to establish that handshake that you have to send these SYN segments back and forth. So let's keep going and kind of look at how each message is constructed at every layer. Now we're not going to talk about layer 1 because layer 1 is just raw signal, whether it's electrical signal, radio waves, light with fiber optic cabling. So we're going to start at layer 2, then talk about messaging at layer 3 and messaging at layer 4, and then 5 to see how the messages move across the network. Remember that messages at every layer are just zeros and ones, but the protocol that's in use may be different. So let's start off with layer 2. So do you know how hard it is to find clip art for Ethernet, like some kind of comic book? This is Captain Ethernet. That's what I'm calling him. I have no idea. I found this clip art a couple of years ago. I love it. So layer 2 is all about the Ethernet protocol. So that's this kind of RJ45 jack that he has for the fist of death here. So let's talk about Ethernet for a second. So an Ethernet frame, we call it a frame because we're talking about layer 2, has a header, has a data field, and it has a trailer. It has all 3. In fact, an Ethernet frame is huge because it contains an awful lot of information. Keep in mind the frame was that blue folder that was holding everything inside of it. So the frame had a packet inside of it, which had a segment inside of it, which had the layer 5 message. Networking is fun message inside of it. So the frame is big. If you're going for Cisco certification, you're going to have to memorize all the parts, every single field, and the size of every single field. You do not have to do that for business telecommunications because, again, the emphasis is on business. I just want you to be comfortable with the fact that at layer 2, inside the frame, the important bit is the destination MAC address and the source MAC address, and the size. These are 48 bits long. Furthermore, the MAC address is in hexadecimal. You should already know this based on homework number 1, where I had you look up your own MAC address. In fact, look up the vendor code associated with the MAC address. The data field, the data is the packet itself, the layer 3 packet information. MAC addresses are 48 bits long. MAC addresses are 48 bits long. MAC addresses are 48 bits long. Test question. We said that, and the Ethernet frame does error detection. It does not do error correction. So here's where I'd like to give you, in class here, picture if you will. Here's what I do in class. I scrunch up a piece of paper and I throw it on the ground like a litter bug, and I walk past it and I point to a student and go, dropped a piece of paper, and I keep on walking. That's error detection. I detected an error. Error correction is I see the piece of paper, I bend down, pick it up, and I throw it in the trash can because that's where it goes. That's error correction. So there's a difference. Error correction is what happens at layer 4 with TCP. It does not happen at layer 2. At layer 2, we don't care about error correction, but we do error detection. So if there is an error, you'll get notified, but it's not going to do anything about it other than just keep retransmitting. Ethernet is very, very chatty. At the risk of a bad joke, here's my intro to layer 3 messaging, and I want to start with IP version 4, which is old school. It's a picture of me in high school. No, it's not, but back in the day, we didn't have iPods. We had to carry our music around, and yeah, so IP version 4 has been around for a long time. It kicked into high gear in the 90s with the internet, but we had IP version 4 in the 80s. We had it in the 70s, and probably a little earlier than that. And we're going to talk about the latest version, version 6. We're skipping over version 5. Yes, there was version 5. It just didn't get ratified as an official RFC. So before we'll get into IP version 6 in class, but just to set the stage for version 4, awful lot of information in a packet. So anytime I say a packet, I'm talking about layer 3. It's written a little bit differently because you'll kind of read this from left to right, and then go to the next row left to right, and then the next row left to right. There's an awful lot of information in here. Bit 0 is the first bit. Goes up, if you can count the bits, 4 plus 4 plus 8 plus 16. This is an odd number because we start counting at 0, not 1. Otherwise this would be 32. But it's 0 to 31, so the first 32 bits is this stuff. And let's see. There is a header checksum, which is how we can detect whether there's an error or not. Again, we're not going to correct the error, but we can detect it. We also have the version number here, whether it's version 4 or version 6, right up front. But clearly the most important part of the packet, the part we care about as network engineers, is the source IP address and the destination IP address. Where it's coming from, where it's going to. In version 4, these are 32 bits long. In other words, 4 octets. So 4 times 8 is 32, a 32-bit address. We'll get deeply into IP addressing. So the data field of a packet is the segment that was stuffed into it. So remember, the segment folder was stuffed into a yellow packet folder. So it might be carrying a TCP segment, and it might be carrying a UDP datagram. So UDP would be, UDP protocols are things like video streaming uses a UDP protocol, Skype and whatnot, just to keep them small, because you can manually retransmit. We don't have to retransmit audio because you can always say, "What?" and the person will say it again. So that's the basics of IP addressing with version 4. We'll get a little more deeply, we'll get a lot more deeply into IP addressing. But to recap, an IP address, an IP packet contains a source IP address, a destination IP address, some checksum information, and the data field is made up of the segment above it, or the datagram above it. And when we get together in class, I will give you a couple of reminders, but then I'm going to jump right into IP version 6, because this is the world you are inheriting. And with that, I will see you in class. Bye-bye.
I know exactly what you need, and I will give it to you constantly. Don't be afraid, just leave it, you'll see. Just put your trust in me.